Hi everyone, this is Indira, Assistant Professor of Institute of Aeronautical Engineering. Already in the last session we have discussed the properties, the definitions and properties of real and complex matrices, right? The very first module of linear algebra and calculus, that is theory of matrices. So the next important topic that we have to discuss in matrices is how to find out the rank of the given matrix. And this concept plays very important role in matrices, right? Okay, so in today's session, we are going to discuss how to find out the rank of given matrix. Now, before going to the rank of a given matrix, we need to understand what is a submatrix and what is a minor of the matrix. Understanding this, that is a submatrix and a minor of matrix, it helps you a lot to understand the rank of the given matrix. Now, let's go with the submatrix. Submatrix, any matrix obtained by deleting some rows and columns or both of a given matrix is called as a submatrix. Okay, just like a subset. Set for if you take any set, a subset is nothing but obtained by deleting some elements of the set. Here also, deleting some rows or columns or both, then the matrix is called as a submatrix to the given matrix. I have taken one example, 3 into 4 matrix, that is a 1, 5, 6, 7, 8, 9, 10, 5, 3, 4, 5, minus 1, which is nothing but the 3 into 4 matrix. That is, we have 3 rows and 4 columns. Now, I have deleted some rows and columns, that is 1 row and 1 column. If I delete, then I got it as 8, 9, 10, 3, 4, 5, which is a 2 into 3 matrix, which is called as a submatrix to the given matrix. Like this, we can quote any number of submatrices for the given matrix. Okay, and this matrix is obtained by deleting first row and 4th column. Right? Now, next is a minor of the given matrix. After deleting some rows and columns, taking the determinant of the remaining matrix is nothing but the minor of the given matrix. Suppose you have 2, 1, 1, 3, 1, 2, 1, 2, 3, 5, 6, 7 is my 4 into 3 matrix, right? And I have taken a submatrix 2, 1, 3, 1 by deleting the last column and last 2 rows. So I got some 2 into 2 submatrix, right? The determinant of this, that is 2, 1, 3, 1, which is nothing but 2 minus 3, which is equal to minus 1, is called as a minor of order 2. Why it is called minor order 2? Because we have taken the determinant of the square matrix's order is 2. Always the determinant we can able to find it out for the square matrix. So the order of the square matrix will act like an order of the element of the minor, right? So here B, which is equal the determinant of B, which is equal to 2 minus 3, which is a minor of the of order 2, right? Okay, now we'll take with another example, 2, 1, 1, 3, 1, 2, 5, 6, 7. Another submatrix I have taken of order 3. What do you mean by order 3? That means we are having 3 rows and 3 columns. Now, determinant of this matrix is minus 8, which is called as a minor of order 3. So, this is how we can understand the submatrix and minor of the element, right? Now, going to the rank. How to understand the rank of a given matrix? Let capital A be M into N matrix, capital A be M into N matrix, right? If capital A is null matrix, we define its matrix to be 0. That means if each and every element of the given matrix is 0, then the rank of such type of matrix is 0, right? If suppose capital A is a non-zero matrix, that means any one of the element is non-zero, then you can call it as that type of matrix as a non-zero matrix, right? Then we can say that R is the rank of the matrix. Then we can call small r as a rank of the matrix if following these two properties are satisfied. The first property that every r plus 1th order minor, every r plus 1th order minor of A is 0, and at least rth order minor of A which is not equal to 0, right? The rth order minor is not equal to 0. Suppose that for any matrix, if 2 is a order, that means 2 plus 1. Third order determinant, minor means nothing but the determinant of the given matrix, right? The third order determinant should be equal to 0, right? Third order determinant should be equal to 0 and second order determinant is not equal to 0. Then 2 is said to be the rank, right? And while denoting the rank, the following properties, that is you have to put it in your, you have to remind that the rank of a matrix is denoted by row of A. Sometimes it is also represented by R of A, capital R of A. Sometimes it is represented by capital R of A, or sometimes it is represented by row of A. Both represents the rank, right? Okay. Now, if rank of a matrix exists, for every matrix we have a rank. For every matrix we can calculate the rank, and it is always unique. We don't have two or three ranks for a single matrix, right? That you have to remember that when you are working out, everybody should get the same answer, right? And every matrix will have the rank. If capital A is a matrix of order m into n, if capital A is a matrix of order m into n, then rank of A is less than or equal to minimum of m comma n. Then rank of A is less than or equal to minimum of m comma n. Right? So that is how we can understand the rank of the given matrix. Right? The fifth property, the fifth note that you can you have to, this is important, that is, if suppose rank of A is equal to R, then every minor of A of order R plus 1 and more is 0. Next, rank of identity element In is its order, that is n is its order. If capital A is a matrix of order n and A is a non-singular, then rank of A is equal to n, right? Another important note is the rank of the matrix is less than or equal to R. Okay, if all minors of R plus 1th order are 0. Okay, the rank of a matrix is less than or equal to R if all minors of R plus 1th order are zeros. Right? Next, the rank of a matrix is greater than or equal to R if there is at least one minor of order R and which is not equal to 0. That means if the rank of a matrix is greater than or equal to R, we can understand that there is one minor of order R, small r, which is not equal to 0. Then only it is possible, right? So that's how the rank of a given matrix can be understood. Now we'll do one. We'll go with one example of how to find out the rank. Randomly, I'll take there is no rule that while finding out the rank of the matrix should be of a square matrix or like this. For every type of matrix where it is possible to find out the rank of the given matrix, right? Now I have taken one example. Find the rank of the given matrix 1, 2, 3, 4, 4, 7, 10, 12, right? Given this, right? 1, 2, 3, 4, 4, 7, 10, 12. First what, when we'll try to find out the determinant of the given matrix. We'll try to find out the determinant of the given matrix. As I have taken only the square matrix 3 into 3 matrix, it's possible to find out the determinant of the given matrix. So the determinant of the given matrix is 8 minus 16 plus 6, which is equal to minus 2. So which is not equal to 0. So we have the minor of, according to the definition of the rank, if R is the rank of the given matrix, if rth order minor is not equal to 0. Here the determinant of third order minor is not equal to 0. 0. Therefore, the rank of the given matrix is 3. Therefore, the rank of the given matrix is 3. Is it clear? Done. So, next is simple example. Another example I'll take. Rank of a matrix 1, 2, 3, 4, 5, 6, 7, 8, 8, 7, 0, 5. 8, 7, 0, 5. Now, given the matrix of order 3 into 4, according to, I have given some note that the rank of the matrix of order m into n is minimum of m comma n. So, it is 3 into 4 matrix. So, what is the minimum of 3 into 4? That is nothing but 3. So, the rank of the given matrix, if it is a rectangular matrix, then the rank is nothing but minimum of 3 into 4, which is equal to 3. So, the highest order matrix will be, the minor will be 3. Okay. So, like this, you can understand the rank of the given matrix. Okay. Now, let us consider the minor of 1, 2, 3, 5, 6, 7, 8, 7, 0. The determinant of the given matrix is 3. Therefore, it is of third order. The rank of this matrix is 3. Okay. Now, if every time finding out the determinant is not possible, because if the matrix is a square matrix, it's easy for you to calculate. Suppose if the matrix is 2 into 2 matrix, we can find out the determinant very easily. If it is 3 into 3 matrix, somehow you can find it out. If it is 4 into 4 matrix, still we can struggle to get the determinant of the given matrix. But it's very tough. As the order of the given matrix increases, the finding out the determinant becomes very tough. Therefore, this method of finding out the rank by using determinants, somewhat it is very difficult if the order of the given matrix goes on increases, right? So, for that we need special methods to find out the rank of the given matrix, and those methods which we are going to discuss is echelon and normal forms. So, in echelon and normal forms, we are going to find out the rank of the given matrix not by using the determinant model, but using elementary row and column operations. So, here, now we have to understand what is elementary row and column operations, right? Interchanging the ith row and jth row is denoted by R1 and Ri. By implication Rj, right? That means the ith row and jth row are interchanged with each other, right? If ith row is multiplied with k, then it is denoted by k into Ri. If all the elements of ith row are multiplied with k and added to the corresponding elements of j, it is denoted by Rj plus k Ri. And these are all operations which you are very familiar in your lower classes. Now, similar operations can be done on the column, and if you know how to do the row and column operations, it becomes very easy for us to calculate the rank of any order matrix, irrespective of whether it is a square matrix or rectangular matrix, right? The corresponding column matrix will be represented, will be denoted by C. And here also, just like a rows interchanging, we can interchange the columns, and you can multiply the column with some scalar quantity k, and sometimes it can be added with some other column, okay, to get. So, these are all nothing but the elementary row and column operations. The elementary operations of the matrix do not change its rank. If you do these operations, the rank of the given matrix never changes. That you have to put it in your brain, because you might get a doubt. Are there so many changes that we are making on the matrix? It may not affect the rank. No, it never affects the rank. Okay, interchanging or multiplying the rows and columns with some scalar, or adding and subtracting the rows and columns never changes the rank of the given matrix. And the rank of the given matrix, if it exists, definitely it exists, and it is always unique. And another thing, equivalent matrix. If B, let us understand the next definition, that is equivalent matrix. If B is obtained from A after finite number of elementary transformations on A, then B is said to be equivalent to A. If A and B are two matrices, equivalent matrix, the rank of A is equal to rank of B. To understand the rank concept, we have taken the definition of equivalent matrix. So, if A and B have same size and same rank, then two matrices are equivalent, right? Okay, so that's how we can understand the rank of the given matrix. So in the next class, what we'll do, we'll try to find out the rank of the given matrix by the very first method, that is echelon form, not by the elementary row or column operations. I don't know, when while determining the rank of the given matrix by calculating its determinant, it will be easy if the order of the given matrix is less than or equal to 3. If the order of the given matrix is greater than 3, then calculating the determinant becomes very tough. So therefore, we need to find out convert the given matrix by either in the echelon form or the normal form to find out the rank of the given matrix. Okay, so that's about the today's section. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.